Hello and welcome. My name is Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Cheng University in Taiwan. I'm also the general chair of this workshop. Behind me I have Ge Tan that was built in 1930 as the second building of then Tainan Technical College, today the National Cheng University. It's now my pleasure to introduce to you our honorary chair, Executive Vice President, Chair Professor Wu, who will welcome you.
It is a pleasure to welcome all of you on behalf of the National Cheng University in Taiwan. I am proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK-D camera together.
Hello and welcome. I am Akram Ashiani, postdoc researcher at the Department of Mechanical Engineering of National Cheng University and assisting chair of this workshop. It is my honor to introduce Mr. Aing, who is currently pursuing the PhD degree in the Department of Electrical Engineering, National Cheng University in Taiwan, under the supervision of Professor Nordling. His research interests include image processing, computer vision, machine learning, and Internet of Things for real applications. He will present deep neural networks and pose estimation to introduce four popular subfields, which are two-dimensional or three-dimensional human pose estimation, head pose estimation, 6 degrees of freedom object pose estimation, and 9-dimensional vehicle pose estimation.
Hello everyone, my name is Aing. I am a PhD student from National Cheng University. My supervisor is Professor Nordling. Now I'm going to be talking about the deep neural network and pose estimation. Here's my outline. First, I would like to introduce the current domains and tasks that the deep neural network contribute to. Second, I would like to talk about the definition of four kinds of pose estimation and how the deep neural networks are applied on them. The last one is the vision of future work. I will provide my personal vision or opinion over the pose estimation. We are living with technologies, and amongst those technologies, the deep neural network plays an important role to perform many complicated tasks. Traditionally, in order to solve the problem, the feature has to be manually extracted and used. Obviously, in the field of the image processing, the edge detection, contour detection, Gaussian smoothing, etc., which are the easy and useful feature need to be extracted. But the tasks which this feature can solve are also simple. However, to solve the complicated work, machine learning such as supporting with a machine, decision tree, gradient boosting, etc. are employed. These techniques are not easy to implement since the target features still need to be handcrafted beforehand, so that it will cause the system become complex. However, the deep neural network is capable not only to solve many complicated tasks, but it also has the achievable system which can automatically extract the effective and efficient feature by its own. There are a variety of domains that the deep neural network can contribute to, such as the computer vision, industrial robotics, medical application, public transportation, etc. Anyway, most of the problem tasks that the deep neural network can perform are 2D, 3D object detection, classification and recognition, semantic segmentation, pose estimation, etc. Among this performance, the pose estimation seems to be given more attention, as it can be implemented to work with real-world applications, such as self-driving assistant, human attention or behavior detection, and object picking appropriation. So what is the pose estimation, and what to predict for it? In the current state-of-the-art research, four kinds of pose estimation can be found, such as human pose estimation, head pose estimation, vehicle pose estimation, and the object pose estimation. Normally, the pose refers to the orientation and translation, but the definition of these four kinds of pose estimation are slightly different according to the constraint and practical application. For example, the human pose can be described by the 2D, 3D skeleton joints. This is because the human has a dynamic action or behavior, and it is not easy to get the exact orientation from the human body. The input to the deep neural network of the 3D human pose estimation is the RGB image or the depth image. The RGB image input contains several scenarios such as a single frame input, multi-frame input, and a multi-view input. A single frame input refers to the single RGB image which has 3 channels. For the multi-frame input, a deep neural network takes a sequence of the RGB image which are usually in terms of the time, because it is believed that those sequence images can be used to train the deep neural network well and obtain the better performance accuracy. The system starts from estimated 2D skeleton joint of each input of the sequence image, and then they are passed through to another deep neural network to estimate all corresponding 3D skeleton joints. Finally, they are fused together by using post-temporal filtering to obtain the best 3D skeleton pose. On the other hand, the multi-view input refers to the image of a single subject taken from multi-different views. This technique starts from predicting the heat map of the corresponding joint, and then from those 2D joints, the fusion is performed to recover the 3D joints. This implementation can improve the robustness to the occlusion, but it might require the camera parameter during the inference stage. To train and estimate the 3D skeleton joints, there are 2 kinds of a training system can be used, such as one-stage training and the two-stage training. One-stage training refers to the direct prediction of the 3D skeleton joints from the input, and for the two-stage training, the 2D skeleton joints are predicted first, and then from this prediction combined with other features, another deep neural network is constructed to output the 3D skeleton joints. For example, in the two-stage training, in the first stage, by using the ResNet 50 as the backbone, the 2D skeleton joints which are predicted from the heat map are combined with the depth ground truth. In the second stage, the 3D skeleton joints are predicted from the first stage feature by using fully connected layer or dense network architecture. By the way, to estimate multiple 2D human pose, there are 2 approaches can be used, such as the top-down approach and the bottom-up approach. The top-down approach is a technique to estimate the 2D human poses person by person by considering the 2D bounding boxes. The 2D boxes are obtained from any human or object detector such as a YOLO network architecture or SSD network architecture, etc. This technique is time consumption since the system has to perform skeleton detection one by one. For the bottom-up approach, the system detects all of the human joints in the image at once and passes them to the post-processing to group the joints and separate the skeletons. For example, from the input of the RGB image, not only the skeleton joints heat map are predicted, but also other features which are called hard affinity fields are predicted. This kind of feature is used to connect joints which are belong together in the same individual skeleton. Finally, all of those heat map and features are passed through to a post-processing called multi-person parsing to estimate multiple 2D human skeletons. For the head pose estimation, the pose can be described by the Euler angle, pitch, yaw, and roll, or a rotation matrix. The most application which this research can apply is in Event Driver Assistance System, ADAS for short. It tries to capture the driver's face and then predict the head orientation. There are two kinds of methods to estimate the head pose, such as the landmark-based method and the free landmark-based method. The landmark-based method is a technique to detect the facial landmark first and then pass those informative landmarks to another deep neural network to request the head orientation. An example from Scene and Tell 19 facial landmarks are predicted from any landmark detectors, and those landmarks are connected to form any adjacency matrix. This adjacency matrix combined with landmarks as a vertex are input into the graph's convolutional network (GCN) a multiple number to estimate three parameters which are pitch, yaw, and roll. The free landmark-based method does not have the landmark detector, but it might estimate some other feature instead. This technique tries to predict the head orientation directly or some intermediate features from which the head orientation can be inferred well. We can take an example of the work from Borghi et al. The depth image which is captured from any sensor is passed through to the deep neural network to estimate the head center. From this head center, the head and shoulder patch can be cropped. The head patch is used to estimate two features, which are the gray feature and the motion feature. Finally, those related head and shoulder features are used to estimate head and shoulder pose. In the current research of the vehicle pose estimation, the pose can be described by 7 or 9 dimensional vectors, which contain vehicle width, height, length, 3 translation vectors in real-world coordinate system XYZ, and the 3 rotation vector pitch, yaw, and rolls. There are 2 rotation angles can be ignored, which are pitch and roll. The reason to neglect this rotation angle is that the roads are assumed to be flat, and the vehicles are assumed not to rotate accordingly. This research is more applicable to the autonomous driving and advent of driver assistance system ADAS. The input to this vehicle pose estimation network can be a single RGB image, stereo image, and a 3D LiDAR point clouds. From the input of a single RGB image, most of the research focuses on predicting the visible and invisible vehicle key points estimated from the heat map, and then those key points are used to estimate the pose directly or indirectly. In this example, the pose is requested directly, and then it is used to project 3D deformation on the image plane to compare with the 2D vehicle key point ground truths. For the indirect method, the predicted 2D vehicle key point can be solved by the PNP algorithm as the post-processing. For taking the stereo image as input, the deep neural network predicts the depth map and then convert it into the pseudo LiDAR point clouds. These pseudo LiDAR point clouds are different from the point cloud generated by LiDAR sensor, where the point cloud can be generated according to the field of view of the stereo image only. Finally, the vehicle pose can be estimated by LiDAR-based detector. 3D LiDAR point cloud can be formulated into any form and then inputted or raw inputted into the 3D bounding box detectors. The reason to formulate the point cloud is related to the invariant number input to the deep neural network and the disorder problem of the point cloud. To have a better performance of detecting 3D bounding box, the point cloud's position are not the only information inputted into the network, but also other features, for example, the surface normal vector of the point clouds. They are concatenated together to form the high-dimensional feature. Finally, a refinement can possibly be added to refine those initial poses. In the research of the object pose estimation, the pose can be described by 6 degrees of freedom, containing the rotation and translation vector. The input to the network can be a single RGB image or depth image. Most of the methods of the object pose estimation can be categorized into 4 types, such as the direct pose method, key point-based method, feature-based method, and the refinement-based method. The direct pose-based method refers to the technique to train and estimate the object pose directly. The network architecture of this method is usually simple and has a fast inference. However, one of the disadvantages of this method is that the estimation can only perform object by object. so that it becomes an obstacle to implement on the real-time application. In the current state-of-the-art method, the object pose is requested directly not only from the input RGB image, but also from the intermediate feature as the post-guided feature. For example, in this paper, the 3D bounding box corner are used as the post-guided feature. Every image pixel has to vote for a unit vector pointing to those predefined 3D corners. Finally, those features are continuously utilized to regress the object pose. For the key point-based method, the main focus is to estimate the object key point and then use them to recover the 6-stop object pose by using a post-processing. Those object key points include 2D or 3D bounding box corners, 2D projected object surface key point, etc. In most of the current methods, those key points are not regressed directly from the deep neural network, but they are transformed themselves to the feature maps, which can be seen in the proposed method of the PVNet. Every pixel in the object must predict many layers of the unit vector. Those layers refer to the number of the key points used, and the unit vector have the direction pointing to those key points. Next, one of the post-processing called ransack key point voting is used to recover the 2D surface key point from those unit vector fields. Finally, the 2D 3D correspondences can be derived and then passed through to the PNP solver to estimate the object pose. This technique can achieve a good accuracy, but it always suffers from the post-processing, which consumes a lot of time. The basic idea of the feature-based method is quite similar to the key point-based method, where every image pixel can have the prediction, but this prediction is different from the unit vector. The feature-based method predicts the individual feature of the target object, for example, the 3D coordinate maps, 2D correspondent maps, surface fragment maps, etc. And then, from those feature maps, there is always a post-processing, which is used to interpret those feature maps to become the global features. And then this last global feature are used to estimate the object pose. For example, in the proposed method of the packet tail, the feature of the 3D coordinate maps is predicted from the generator of GAN to for the discriminator. This 3D coordinate maps is just only the object's texture projected from the object coordinate itself in the 3D space. These feature maps are used to combine with the corresponding 2D coordinate to form the 2D 3D correspondences, and then they are passed through to the PNP ransack to estimate the 6-stop pose. This method cannot obtain the accuracy as good as the key point-based method, but it can be developed to estimate the multiple object pose faster than the key point-based methods. The main idea of this refinement-based method is to iteratively refine the initial pose by estimating the pose offset. You can see in this example. From the initial pose, the system renders an image by using the CAD model, and then pass it to the deep neural network with the observed image to estimate the pose offset. This pose offset is combined with the original pose to form up another initial pose for another iteration estimation. This kind of technique can have a function of trade-off between the accuracy and the inference speed. Moreover, this technique can be used as the extra refinement module to attach on any other pose estimations. In most of the object pose estimation systems, the network architectures are composed of encoder-decoder modules, 2D convolutional layers, and fully connected layers. The encoder-decoder module contains two subnetworks, which are the encoder and the decoder networks. The encoder network refers to the pre-designed network module, which uses any existing architecture as the backbone, and the decoder network refers to the upsampling feature from the encoder until reaching the desired output. The encoder can be adopted from the well-known ResNet network architecture, DenseNet, EfficientNet, etc. And the function of this module is to extract effective and efficient intermediate feature so that the following deep neural network can estimate the output well. 2D convolutional layers are always used to request the output feature maps or to predict the attentional maps. These layers stand independently from the encoder-decoder module, and their dimension vary according to the desired output feature maps. For fully connected layers, they are always used to request a direct object pose containing 3 rotation or 4 quaternion parameters and 3 translation parameters. Last but not least, there are 3 learning styles have been adopted in all of the methods of the object pose estimation. They are supervised learning, self-supervised learning, and the reinforcement learning. The self-supervised learning is the most well-known learning style which has been used in this day. Given the input, the deep neural network is trained and output the desired feature to compare with the ground truth by using any loss functions. The desired feature output and the ground truth can be direct and indirect poses. The direct poses refer to the 6-stop object pose containing 6 or 7 parameters, and the indirect ones refer to the feature maps generated from the poses. All the methods using the supervised learning are quite simple and straightforward, and can always achieve the high accuracy performance. The method using the self-supervised learning do not require the 6-stop object pose ground truth. What it does is to estimate the direct object pose and then generate the corresponding object feature to compare with the observed ones. For example, in this paper, the predicted pose is used to generate a render RGB image, mask, and the depth. In each render feature map, there are several features are used to compare, such as light agnostic, structural similarity, perceptual similarity, etc. The performance of using this self-supervised learning is quite low compared to the supervised learning method. But this method is more applicable to the real-world application since the pose ground truth is not always available. For the reinforcement learning, it can also be applied to the object pose estimation, where the input image is used as the observed environment and the predicted pose is considered as the action. The deep neural network, which is known as the agent, takes the feature maps as the state of the observed environment to produce the action. This action refers to the rotation and translation in 6-dimensional space, and then it is used to generate the next state of the environment again. This step is repeated until reaching to the target state. The reward can be calculated from the observed state and the predicted state. This reinforcement learning is quite new to apply on the object pose, but the performance is not quite bad compared to the supervised learning. To be noticed that most of the methods above can be used to estimate a single pose only. In order to estimate the multiple poses, the system has to be attached with any object detector first and then estimate the pose object by object. For estimating the multiple instant object poses, Aing proposed an end-to-end system which can be categorized as the bottom-up approach, supervised learning, and feature-based method. It is the bottom-up approach because it estimates all the features at once and then uses them to estimate all poses simultaneously. Since using the pose ground truth to generate the feature map, it is categorized as the supervised learning method. It is one of the feature-based methods because every image picks up a predict feature which is related to the object itself. This proposed feature-based method combines 2 significant features, such as the pixel-wise voting technique and the extension feature of the 3D coordinate maps. Given an input of a single RGB image, ResToNet is used as the backbone, and then output four kinds of feature maps for all multi-instant objects at once, such as the arrow mask, semantic segmentation mask, center vector maps, and the 6D coordinate maps. During the inference, post-processing is used to group and separate the feature and instant object by firstly combining the arrow mask and the semantic object mask to produce the refined mask, and then cooperating with the center vector maps to determine the instant object mask. Finally, those instant masks are merged with the 6D coordinate maps to form up 2D, 3D correspondences with random selection, depending on the object size. Last but not least, those predicted instant 2D and 3D correspondences are imported into the PMP runtime to estimate the instant 6-star object poses. From the experimental result, this proposed system outperformed the other in the 3D transformation matrix with the least time consumption. Here are the accuracy performance on occlusion line model dataset. There are three metrics used to evaluate the system, such as the 2D Pro, ADDS, 5CMD, which are the performance of the 2D projection error, 3D transformation error, and the 5 cm 5 degree error. As we can see that the performance of the ADDS and the 5CMD of this proposed system outperform the others. Here is the time consumption performance on occlusion line model datasets. We can see that this proposed system consumes only 39 milliseconds per frame for 7 instant objects. Here is the application study on the randomization of the voting hypothesis and the PNP candidates. In the bottom part of this application study, the author also compared this proposed system with the method using only the feature of the 3D coordinate maps. Even using the ground truth of the 3D coordinate maps to estimate back the 6-star object pose, the accuracy performance obtained can just only achieve 82% in the 3D transformation matrix. However, when using the proposed 6D coordinate maps, the performance can be boosted up to 98%. Here are some examples of the 6-star object pose estimation on occlusion line model dataset. The orange and the green projected 3D bounding boxes are the prediction and the ground truth, respectively. The future challenging work of the human pose estimation is predicting the multiple 3D skeleton in real time. To achieve this, the multi-view input images are used to predict all 2D skeletons of each view first, and then fuse them to become multiple 3D skeletons by using a post-processing or convolutional neural network. Seeing an RGB image is not applicable to estimate the head pose at night time, except the depth map. More feature maps from any other sensor are considered, such as the infrared or thermal image camera. For the vehicle pose estimation, the combination between the input of the LiDAR point clouds and the RGB image will become widely used in the future to perform 3D bounding box detection and object classification. Scene training with the RGBD image to estimate the object pose provides a high accuracy, but the depth map is sensitive to the outdoor scene and some material. The stereo image can be used to predict and replace the depth channels so that the high performance can be kept for all conditions. The future work of the object pose estimation will become more broad, where the deep convolutional neural network can detect the general object poses which are in the same category by training on the various synthetic datasets. These datasets, which are generated from the CAD model, contain a variety of rigid objects with many different poses. This is the end of my presentation. Thank you for your listening.
Hello, Mr. Lian. Hello, everyone. Welcome to join our Q&A session. Thank you very much for the great talk, and thank you for willing to join us online. We have gathered all the questions from the YouTube chat. Let me speak them one by one for you.
Okay.
So the first question is from Jacob. Hello, I want to know the performance comparison of top-down and bottom-up method. Thank you.
So actually, the top-down has a better performance. It always has a better performance because that one, they just detect one by one. So and the model also separate. So that's why the top-down always has the better performance. So for the bottom-up, the benefit of using the bottom-up is the time consumption. So actually, the bottom-up can overcome uh, the the much time consumption, which means that it can process in real time, something like this.
Thank you. Another question is also from Jacob. He say also how to evaluate 2D, 3D post estimation.
Oh, to evaluate the 2D post estimation. So actually we have many kinds. For example, in the human post estimation, so they just take only the human joints. So which means that what they do is just to calculate the error of the 2D human joints. So the error is in pixel, so in 2D. For the 3D, the error must be like the unit of the 3D is a centimeter or the meter. So we have to calculate the real human joint in 3D space, in the world 3D space. And this one is just only for the human post estimation. And for the vehicle pose or maybe the object pose, we have a different evaluation metric. And then I take another example of the object pose estimation. So in order to evaluate the 6 of object pose estimation, so we use a 2D 2D projection error. This also referred to the 2D pixel and 3D transformation, which means that they just use a point cloud and then transform it and then calculate the different error, something like this. And then another is 5 centimeters, 5 degrees, something like that. So I can answer that to evaluate the 2D, 3D post estimation. So we have many different kinds to evaluate them.
Great, thank you. Another question from Depeche. So entrepreneur Elon Musk was against the LiDAR sensor for the use of autopilot, but recently Tesla started experience with LiDAR sensor with their car. Do you know what led him to change his decision?
So actually, I just heard the news from the Tesla. They say that he has failed to detect the car that collapsed in front of the autopilot car because of the car is inappropriate behavior. Just like when it's collapsed, the RGB camera cannot detect that one is a car. That's why this crash. That's why the Elon Musk or maybe the Tesla company just consider again about the LiDAR point cloud, because the LiDAR point cloud, what it can do is just only to detect the object. So actually they have different advantages. So RGB can detect many things like category or maybe the other sign of the traffic, something like this. And then the LiDAR sensor can detect only the object, but it's very accurate. That's why I think Tesla would like to transform, or maybe actually it's not transform, it's just like to add the LiDAR sensor, or maybe the LiDAR point cloud onto the RGB image as a source information to detect the object.
Thank you for the detailed explanation. For the audience, I just saw somebody want to join our Google Meet channel. Just let you know, to avoid complex problems, to avoid messy, please just put your question on the chat. Both the YouTube chat and Twitch chat will be good. Okay, the next question. Thank you so much for your presentation. Would you please explain more about the generator and discriminator and their relationship in the feature-based model?
Yes. So actually, the generator and the discriminator is just like when we play the ping pong. So we have the striker, and then we also have the survivor, which means that the striker one would like to shot, and then the survivor would like to survive the ball. So after time, which means that after they just predict time by time, so the striker will become the very professional striker, and then the survivor will be professional in surviving, which means that so they both are in professional, but in testing for the again, we use only the generator to fool the discriminator. So the function of the generator is to fool the discriminator, and then the discriminator try to distinguish uh, the image, the input image is the fake or the real or something like this. Yeah.
Okay. Next question. It was nice to see different methods for post estimation. Which one of the models introduced for the post estimation is more robust?
So sorry again, I cannot hear clearly.
Which one of the models introduced for the post estimation is more robust?
Can you repeat the whole question? I cannot get from the beginning.
So in the beginning, say it was nice to see different methods for post estimation. Which one of the models introduced for the post estimation is more robust?
Oh, so actually it depends on the input point, the input source. I mean the input information. For example, RGB is very challenging. So actually, but it has less source information than the RGBD. So which means that the RGBD can do better, can achieve the higher performance than the RGB. But the RGBD is uh, just like not the very not the best. The light point cloud can do better than the RGBD because the light point cloud can detect outdoor, also the indoor, something like this. But RGBD can work in only the indoor. So that I can answer that the post estimation accuracy depend on the input source information.
Okay, thank you. Is vehicle post estimation only for cars, or will it be work for scooters, bicycle, motorcycle, and how will the joint define in it?
Okay, thank you for your question. So actually, again, it depends on the source information. So for example, so actually the scooter, the bicycle, the vehicle are the rigid object. So if we provide enough data set to the neural network, it can detect well. For the bicycle, it has maybe the human, right? So in order to detect the pulse of this one, it's quite a little bit harder. And then motorcycle, the scooter is also the same. So in order to answer this question, actually, I can say that the process it can detect detect well unless we can provide the data set to the neural network. So right now we can have only the vehicle data set. But if in the future we have the scooter or maybe the motorcycle data set, so that we can also detect them well.
Great, thank you. Another two questions from Esteban. The first one is, are there Taiwanese companies that use this?
Sorry.
Are there Taiwanese companies that use this?
Oh, I'm not sure about this one. Actually, now I'm in the university. I think I haven't I have no experience about in the Taiwanese company, so I cannot answer this question. Sorry.
No problem. Another one, post estimation for human body and face What about specific body parts such as hands?
Oh yeah, actually that one is also the pose, the hand pose actually. Actually, I would like to also include this one, but I have less information about this one, and then I decided to exclude this one. Actually, the hand is also the pose. The pose which means that we try to uh, see the orientation, but actually the hand is not easy to get the orientation because it has a dynamic behavior. So a hand is also the pose estimation.
Thank you. A question from Oscar. Amazing presentation. I want to ask question. Why in multi-person case, single stage methods are less developed?
Actually, they are developed equally actually. Some methods use a single stage, some methods use a multi-stage. It depends actually. So, but we have to think about our application. So what application or what the area that we apply our research to. For example, in the human, 2D human pose, in the multiple 2D human pose, we would like to apply to get maybe in the crowd people application, so that we need a very fast inference time, so that we use only one stage, a single stage, to detect the multiple human pose or something like this. But actually, that one suffer from the accuracy. The accuracy is quite low compared uh, to the top-down approach or something like this.
Thank you. I just saw another question from Esteban. So he first quote the vision of future research, then ask how many cameras for multi-view in point one.
Actually, there are only two cameras. Yeah.
Another question from Raven. Thank you for sharing an overview on post estimation with us. Is there any difference between the computing efficiency of top-down and bottom-up methods?
So sorry again. I'm sorry.
So the question is there any difference between the computing efficiency of top-down and bottom-up methods?
To 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 calculate the accuracy, actually, they are the same. The difference just only uh, the, the method that they use to regress or maybe to predict the pose. So top down and the bottom up has the same accuracy calculation. Yeah.
I think her question is about the computing efficiency. So I guess it's more like computational time it take for both the top-down and bottom-up.
Oh, sorry. So the computational time of the bottom up is always better, because it just predict only one, which means that it predict all the features at once, and then separate them. But for the top down, it has to apply the object detection first, or maybe the human detection first, and then one by one. So apply on uh, the 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 post estimation system. So actually, that also require a large memory to store all kind of uh, models also. So actually, the bottom up approach is better, but it's not better in accuracy.
Great, thank you. I think that one is the last question. We still have some few minutes, so maybe we just wait for a few minutes to see if any audience have more question. Please feel free to put on the YouTube chat. Also, we got some comment from YouTube chat, like from Jacob. He said, "Thank you for explanation." And from Lai Wenren, say, "I also changed my direction from stereo RGB to LiDAR plus RGB due to high ranging accuracy of LiDAR." Okay, let me check.
Is there any question?
We don't have questions from Twitch, so maybe we'll just wait for a few minutes.
Okay.
Yeah.
I suppose that you had a question, but I cannot understand.
Okay. No problem. Let's see. And also just for just information for the audience, we will have also the workshop tomorrow 4 p.m. and this Friday we will have our hackathon session. Okay, I saw some question from Oscar. The question is, which method is the best for post estimation in age device?
Which method is the best for post estimation? Actually, I have no idea about this one. Maybe you can ask again, but more specific. But I cannot answer this one. Sorry.
So mention in age device, maybe also
Age device.
Yeah. Also send this sentence to you.
Sorry, I have no idea with the age device.
Okay. So the audience, do you have more questions? Please feel free to put on the YouTube channel. Okay. Okay. Now I see another one. Depends on the model size and GFLOP required for each specific method. Oh, I think he's trying to answer the question from Oscar.
Oh, okay.
If there's no other question, I think now is a good time to end it. So thank you so much for all the answers. As I mentioned, we will have another talk at tomorrow 4 p.m. So look forward to seeing all of you. Thank you, everyone. Thank you, Mr. Lian.
Thank you. So actually, I'm sorry for my hearing. Sometimes I cannot hear clearly.
Also, sometimes my microphone problem. So yeah, don't feel sorry for that. Yeah, thank you so much.
Okay, thank you.
Bye.